Hello, my dear students. Today we are going to learn Newton's second law of motion, which is a topic of chapter Laws of Motion, class 9th, Physics, ICSE board. In this video, we will cover the topics Newton's second law, its definition, derivation of mathematical form of Newton's second law, its applications in our day-to-day life, and some numericals related to it. Before this, you know that Newton's first law of motion defines force only qualitatively. It tells us that physical cause which changes the state of motion of a body when it is applied on it is force. It does not tell us about the quantity of force, how much force we require, what is the formula to calculate that force. It is Newton's second law of motion which gives us the quantitative value of force. It relates force to the measurable quantities like acceleration and mass. Let's start with mathematical expression for Newton's second law of motion, that is F is equal to ma. Newton proved experimentally that on a body of mass m, when a certain force is applied, it produces an acceleration in the body, and the force applied is directly proportional to the mass of the body if the acceleration remains constant, and acceleration is directly proportional to the force applied if the mass remains constant. Based on these two concepts, two graphs were plotted, which were the experimental results as given by Newton. First graph, as you can see, is related to A is directly proportional to F. F is taken on x-axis and acceleration A is taken on y-axis. It says that if two masses are same, two bodies having the same mass are to be accelerated, then we have to apply more force if we want to accelerate a body more than the other. So acceleration is directly proportional to force applied. Second, now we will consider that the two bodies are different, masses are different. One is a heavier body, another is a lighter body, and you want to produce same acceleration in the two bodies. Let us say one is a tennis ball and one is a football. So definitely, if you want to make them move with same acceleration, then you have to apply more force on the heavier body to make it move faster. So what conclusion is drawn from it? We understand that F is directly proportional to M. You can see from here that if we take mass on x-axis and force on y-axis, then the sketch obtained is a straight line inclined towards x-axis. When we combine these two results, these two experimental results, we get F is equal to kma. K is the constant of proportionality here. The unit of force is so chosen that K becomes 1 when M is equal to 1 and A is equal to 1. So from here, we will define that how much is 1 unit of force. Unit we will define later. Unit of force is Newton. So how much will be 1 unit of force? That amount of force is taken as 1 unit of force, which when applied on a body of unit mass produces a unit acceleration in the body. So accordingly, we take K is equal to 1. So what is our final expression? We get F is equal to ma. Children, to know about the other form of Newton's second law, we come across a term which is called linear momentum and can also be called as only momentum. No need to add the word linear every time. Let us understand what is linear momentum. It is our common experience that if two bodies of different masses, again I will consider a tennis ball and a football, if they are moving with the same velocity and they are brought to rest in the same time, then the force needed to stop the football will be more than the force needed to stop the tennis ball. Similarly, if you take two footballs, if two bodies of the same mass are moving with different velocities, that means one football is moving faster than the other, then to stop them in the same time, the force needed for the faster football is more than the force needed for the slower moving football. So what do we conclude from this? We understand that the force needed to stop a moving body in a definite time depends both on the mass of the body and its velocity. Actually, the force needed to stop a moving body depends on the product of mass and velocity. This product of mass and velocity for the moving body is called its linear momentum, or simply momentum. It is denoted by the letter small p, and P is equal to mv. This is the formula for linear momentum. So we calculate momentum for a moving body. It is a vector quantity and its direction is along the direction of motion of the body, that is along the velocity of the body. SI unit kg meter per second, CGS unit for momentum gram centimeter per second. Now let us study change in momentum. Now change in momentum of a body can be either due to the change in mass of the body, or due to change in velocity, or due to change in both the mass and velocity of the body. So we write change in momentum as delta P is equal to delta mv. Both are having delta in front of them, mv. Here symbol delta stands for, also called del, stands for a small change. So if we write delta P is equal to delta m into v, does that equation apply to all the conditions around us? No. This equation is applicable in case of atomic particles only, because that equation, the equation delta P is equal to delta mv means that mass of the body is also changing. But children, mass of the atomic particles only change when these particles move with a velocity equivalent to velocity of light. And what is the factor by which the mass changes? It is by this formula we can find out. M is equal to m naught upon square root 1 minus v square by c square. What is m naught? M naught is the rest mass, mass of the body, mass of the particle when it is at rest. Okay, so we should say that delta P is equal to delta mv is applicable only for atomic particles moving with velocities greater than the velocity equivalent to the velocity of light. Then what about other particles? For all other particles, mass should be considered as constant if the velocity of the particle, if the velocity of the moving particle is less than 10 power 6 meter per second. If the velocity of the moving particle is equivalent to velocity of light, then only its mass will change. And for all the particles around us, it is very difficult to attain that. Even attaining a velocity as large as 10 power 6 meter per second is also very difficult. So for all other particles, we cannot write delta mv, we will write it as m into delta v. So how do we denote change in momentum for a body around us? Not microscopic bodies like atomic particles. For the bodies around us, which we can see with naked eyes, it is delta P, change in momentum, is equal to mass multiplied by change in velocity. Now let us find out change in momentum in a given time, which is called rate of change of momentum. Now, actually, when a force is applied on a body, on a moving body, its velocity changes. Either the body stops or the body attains a greater velocity, starts moving faster. So when a force is applied on a moving body, its velocity changes. And due to change in velocity of the body, its momentum also changes. So in a given time, we will find delta P upon T. Rate of change of momentum expression will be, you write it as m into delta V upon delta T. If you see this expression, delta V upon delta T, then it is telling you about change of velocity per unit time. And you have studied the definition of acceleration. Acceleration is change of velocity per unit time. So in place of this expression, we will write m dot A. Therefore, what is the formula for rate of change of momentum? It is equal to m into A, mass into acceleration. And also, by Newton's second law of motion, we know that F is equal to ma. We have derived this equation. So from these two equations, what do we obtain? From which two? F is equal to ma and delta P upon delta T is equal to ma. We get F is equal to delta P upon delta T. This is the general form of Newton's second law of motion in terms of rate of change of momentum. And what is the most popular form of Newton's second law of motion? It is F is equal to ma. So what is the statement of Newton's second law of motion in terms of change in momentum? According to Newton's second law of motion, the rate of change of momentum of a body is directly proportional to the force applied on it, and the change in momentum takes place in the direction in which the force is applied. Newton's second law is the fundamental law of motion. It explains all things about a moving body, the force applied, momentum, acceleration, many things. So it is considered as the fundamental law of motion. And in the first law of motion is also included in the second law. And we can derive third law also using this. Let us see the first law. It is that we know that F is equal to ma. So from this formula, if we write F is equal to 0, A will also become 0. So that means no force applied on a body, acceleration will not be produced. This is the statement of first law, that a body will remain in the state of rest or in the state of motion unless an external force is applied on it. Thus, our relation F is equal to delta P over delta T is equal to ma. It holds good under two conditions. First, when velocities are much smaller than the velocity of light and when mass remains constant. And this defines our Newton's second law of motion. Now let us study a few applications of second law of motion. You know that the formula says F is equal to delta P upon delta T. This mathematical form can be written as delta P is equal to F into delta T. So a given change in momentum on a body can be brought. We can bring change in momentum of the body either by applying a large force for a small duration or by applying a small force for a longer duration. Based on this, let us understand that while catching a ball, why does a cricketer withdraws his hands along with the ball? You must have observed that. When the ball is hit by the batsman, it starts moving very fastly. The fielder has to catch the ball and bring the momentum of the ball to 0. Now, if the cricketer does not pull back his hands and stops the ball as soon as it touches his hands, he uses a very little time to stop the ball. Then the force exerted by the ball on the hands of the cricketer or the fielder will be very large, and that may hurt his hand. But if he pulls his hand back along with the ball, then he takes a longer time to stop the ball. and this will reduce the effect of force exerted by the ball on the hands of the cricketer. Thus, he avoids a chance of injury. Another application is that athletes often land on sand after taking a high jump. Reason can be explained on the basis of our Newton's second law of motion. F is equal to delta P upon delta T, or delta P is equal to F into delta T. Actually, when an athlete lands from a height on a hard floor, he may hurt his feet because his feet come to rest instantly, immediately, as soon as he touches the floor. So a very large force is exerted by the floor on his feet. But on the other hand, when he lands on sand, his feet push the sand for some distance, and the time duration in which his feet comes to rest, it increases. As a result, the force exerted on his feet decrease, and he is saved from getting hurt. Also, the third example we will discuss, that is, glass vessels break on a hard floor, but they do not break on a carpet when they fall on them. Reason is the same, that when they fall on the hard floor, they come to rest instantly. Time duration is very less, so the force applied by the floor on the vessel is very large and the vessel breaks. But if it falls on the carpet, then the time duration in which the vessel comes to rest increases as the carpet is compressed, and the force exerted on the vessel by the floor is very less and it does not break. Now let us do a few numericals related to Newton's second law of motion. These numericals I have taken from your Concise Physics by Selina, page number 70, and question numbers are according to the book questions. Question 1 is, a body of mass 5 kg is moving with velocity 2 meters per second. Calculate its linear momentum. So given is mass is equal to 5 kg and velocity is equal to 2 meters per second. You know the formula for momentum. Momentum is equal to mass into velocity. Substitute the values and you get momentum as 10 kg meter per second. Question 3. A force of 15 Newton acts on a body of mass 2 kg. Calculate the acceleration produced. Here force is given 15 Newton. Mass is equal to 2 kg. You know from Newton's second law of motion, F is equal to ma. From here, find out the formula for A. A is equal to F by m. Substitute the values. A is equal to 15 by 2. So that is 7.5 meter per second square. Question number 6. A force of 10 Newton acts on a body of mass 2 kg for 3 seconds, initially at rest. Calculate first the velocity acquired by the body and second, change in momentum of the body. Let us see the quantities which are given. F is equal to 10 Newton. 10 Newton force is given, mass given 2 kg, time is given 3 seconds, and it is said that initially the body was at rest, so we will consider u is equal to 0. Now we have to find out the final velocity. For that we will use the formula F is equal to ma. A will be written as v minus u, final velocity minus initial velocity upon time. So u will be 0, it is given, v minus 0 upon t into m. So what is our formula becomes? What formula we get? It is F is equal to mv upon t. What is v here? Then take t to the numerator on left hand side, m to the denominator on left hand side. So we get v is equal to F into t upon m. Substitute the values, solve it, and we get v as 15 meter per second. Second part is find the change in momentum of the body. So we know that other form of Newton's second law of motion is F is equal to delta P upon delta T. From here obtain the value of delta P. it is equal to F into delta T. Substitute the values. F is 10, T is given as 3. So we get delta P as 30 kg meter per second. Children, these were a few numericals and the method to solve them. I hope you have learned a lot from here. Thank you.